Hello everyone. So today I'm going to talk about bio-inspired neuromorphic devices based on organic electronics. So going forward, I would like to discuss what organic electronics is. So organic electronics is a branch of chemistry where the chemists design, synthesis, and characterize organic molecules, which the molecules are actually flexible. The molecules can be solution processable, synthetically tunable, and also biocompatible. Now, these organic molecules are specifically of two categories. One which has small molecules, which corresponds to the class of materials that are being shown here. So these are comparatively small in size. So it's just a molecule and there is no repeating units involved in these structures. But this one more interesting class of organic molecules, which are polymers, specifically conducting polymers, which are very useful for several applications. So if you might have noticed that like the polymers here, you can see that there are structures which repeats itself, and that is why they are called polymers. And they are actually consist of small molecules which are combined together to actually form larger molecular structure, which helps to actually get conduction properties out of it depending on the environment and the processability and the synthetic tunability which has been gained during the course of the synthesis of those materials. Now, these materials can find several applications. Some of the applications are shown here, where it is actually being used in organic solar cells, organic light-emitting diodes, some thin-film transistors, electrical devices, and even in recent times we can see actually those bending phones. So those phones are also of a kind. Those screens are actually polymers, which are very flexible, and hence we are getting those kind of other interesting applications. So going forward with the organic electronics, and since we are going to talk mostly about the polymers, so we should know like what are these polymers. So the polymers that we're going to use are conducting polymers or semiconducting polymers. And in this case of polymers, these can actually have properties of electronic conduction and ionic conduction at the same time. So if you can see from the video, the GIF file here, you can see that there is a kind of electronic charge carrier transport into the polymer, and also there is an ionic transport which occurs along the vicinity of the polymer. So this kind of polymers which can have mixed conduction, the conduction involving electronic charge carriers and also ionic species, these are called organic mixed ionic electronic conductors. And how does this operate? This is very important to know, like how does this operate, because that will help us to analyze and understand like how it can be used in several applications. So going forward, I'm going to show like what are the how it operates. So suppose you have a conducting substrate, and on top of that, you actually coat the polymer, and then you dip that inside an electrolyte. Now, the conducting substrate is actually connected to the working electrode of your potentiostat or your any device with the device that you want to analyze, and then you have a counter or reference electrode in your electrolyte. Now, whenever you apply a positive bias on your or through the working electrode on your substrate, then your polymers can get oxidized. So depending on the kind of species, the kind of molecules that are present in the entire polymeric backbone, it can get oxidized. And since we're oxidizing it, then due to the charge imbalance, anions which are negatively charged gets injected into the polymer film. And this is what happens at the heart of the conducting polymers. And since we can see that upon the application of a stimulus or application of a potential, there is a change in the conductivity of the polymers, and there is an ionic insertion into the polymer backbone. Is somewhat is like the behavior that we see in neurons, especially during the generation of action potential. So what happens is that we can actually use this kind of polymers for several applications, specifically in mimicking neurons. In neurons, we know that the kind of the action potential that is being generated, and when it moves, there is a stimulus, and due to the presence of the sodium potassium pump, there is an imbalance which occurs across the bilipid membrane, and due to the changes in the concentration, and a change in the voltage occurs, and that is what drives the action potential. So similarly, on the same grounds, we are actually seeing the same thing which happens in the conjugated polymer or the conducting polymers, where with the shuttling of the ionic species, there is a change in the conductance of the polymer. The same thing is also seen in an axon, and that is why we can compare that the polymers actually are capable of behaving like neurons if we can actually make some proper devices out of it. So there is a class of devices called neuromorphic devices that are used, or we can mimic the brain with it. For example, if you suppose that as a human being, we can actually do simultaneously image processing, speech recognition, audio classification, cognition, balance, etc. But the amount of energy that we consume is very, very less. Whereas if we compare that with neural networks or in computers, it consumes too much amount of energy for it to operate, to actually get some output out of it. So if you can see on a neural network here, it's actually just like processing. So this neural network is solely for image processing. And if you want to incorporate speech recognition, the number of input nodes and the output nodes vary a lot. So based on that, it's very important, like the kind of the coding that you perform in a software. But despite that, there's a huge amount of energy which is involved in these systems. But if we can make neuromorphic devices, those can actually mimic the brain, and it's a hardware form of the neural network, which is a software analog of the same thing. So if you can go to the hardware analog, so you can actually use several kind of devices. Most commonly, the devices that are being used are the memristor based ones, and you can incorporate that into electrode arrays as chips, and then you can perform several kind of operation onto it. For example, the most common one being is a dot product engine, which can be done using the kind of circuits that is being made, or the chip that is being made using those materials. But the interest of what I'm going to talk about are the effect of polymers and using polymers in mimicking the brain. So since I have already introduced like the effect of ions in these systems, especially with the polymers that I'm going to talk about. So in real neurons, in axons, we know that there's a shuttling of ions. The same thing also happens in the polymers. So that will be an amazing tool, amazing class of devices that we should explore to get closer to the kind of behavior that the neurons have. So these are class of transistors called organic electrochemical transistors, where we use those polymers as our channel material. So here is a diagrammatic representation of the organic electrochemical transistor, where you have the source and drain electrode, and between the two electrodes you have the channel material, which is the polymer that I'm talking about here, and then we gated with an electrolyte which is like the same physiological concentration of electrolytes, and or can be just be sodium chloride solution in water, or KCl or potassium chloride, anything. And then you can use a gate electrode, which most commonly ones that are being used are AgCl pellets. And with the circuitry here, you can actually incorporate or dope the polymers here with the ions, and then you can tune the conductivity of the channel and get the transport characteristics out. So here is a diagrammatic representation of how the transfer characteristic looks like. And here is the yeah. So here is the video, and here you can see that whenever the device turns on, the ions are getting injected into the polymer, and then the channel becomes conducting. So this is how it operates. So this kind of devices, you can actually play with the materials at the gate, or even play with the semiconductor channel, or the polymer channel here, and then you can actually mimic neural activity, and or you can use impedance to sense electrolytes, and also you can functionalize the gates for specific analyte detection. And so you can actually tune the entire architecture as per your needs, and based on the changes in the circuits that you design with by playing with the connections, you can actually try to mimic the neurons, of which the inverter 1A could be like the starting point for understanding like how the OECT can help in mimicking the brain. So going forward with logic gates, which is the same thing as an inverter is a NOT gate. So with the devices, with the OECT devices that we have, we can actually make the connections and perform logic operations, which could be NOT and or NAND XOR gates. And here is a diagrammatic representation of how the inverter operates. So the connections for an inverter, and you can see that here we have a p-type OECT and an n-type OECT. Where in p-type the charge carriers are holes, and here the charge carriers are electrons. So since the holes are the charge carriers, so anions gets doped into it, and the polymer can get oxidized. So there is an excess of holes in the system, and then it can start conducting. And here those are the electrons which are conducting in the system. And these are the kind of polymers that are being used here. And upon operation, we see that as we increase the V out, the current starts, the voltage, as we increase the input voltage, the output gets lower and lower. So for higher input, the output gets lower. So that is how an or not operation be performed using OECTs. And here we have the gain versus V in plots for the same. Now, if you might have noticed that the transfer characteristics here is like almost the same as a typical transistor, but if you are more careful, you can notice that the voltage windows are extremely low. The reason for you, there are two reasons for it. First of all, since we're using polymers and there's a doping where by driving the voltage at the gate electrode, we can dope the polymer very easily because of its oxidation state. And secondly, the advantage that we have with this is that we're operating well below the stability window of water. So we can even mimic the brain-like behaviors in water in the same electrolyte concentration without affecting anything or without water electrolysis. So in this way, this kind of devices are very useful where it can actually perform neuromorphic operations or logic operations in this case. And that too, it can do that in ambient condition, even in the presence of water, where the electrolyte is anyways water. So here we have a NOT gate. So now I'm going to talk about an XOR gate kind of an operation here, where we see as far because we know from the truth table that with the 0, 0 and 1, 1 operation, we see no output. But when the input is 1, 0 or 0, 1, we see an output here. So that is what an XOR operation performs, and that is what we see here. Now, how does this material or this or kind of a circuit or this OECT is capable of performing this kind of behavior? It's solely because of the material of interest here, which shows a transfer characteristic which looks something like this. So here with increasing the voltage, the current starts rising up to a particular voltage and then it starts coming down. So there is this negative differential transconductance region which occurs here, and that is what helps in mimicking the XOR operation, where if your inputs are of low voltages, then the operation is off, the device is off, and if the voltages are too high, the device still remains off. But if there is a mismatch between the two inputs, where the voltages are within this window here, then it gives a current output, and that means that the device is active. So there is no operation in these two regimes, but in this case, it actually behaves like an XOR kind of an operation. So if you are very careful with the kind of structures here, you might know that this is how the kind of behavior that we see for the sodium and potassium gates in sodium potassium pump. So can we employ this and develop an Hodgkin-Huxley model with it? Yes, we can. So there's a paper that's been published in Nature Materials where the same material was being used, and with that they were able to mimic the action potentials of the as we see in an axon. And here is a diagonal representation where this dark line, the black colored line here represents the entire action potential that can be seen by using the circuit here, where we have two OECTs, one that is a potassium OECT and another one is a sodium OECT. So based on these two and the circuitry here, you can see that that this thing actually behaves almost like an action potential, and that was very fascinating that it can that the material, the BBL material that shows this kind of plot, Gaussian bell-shaped plot, is actually helpful in building the Hodgkin-Huxley model and also mimic the action potential that it generates. Furthermore, if you closely look at the circuit here, and they actually just apply the current continuously, and if you do that, you can actually generate with a constant input several pulses. So these are a continuous pulsing which occurs in this device in this circuit, and if you can increase it, then you can see that the current also increases. So yeah, so this is how the Hodgkin-Huxley model that was developed using OECT behaves, and it can also show subthreshold oscillations, coincidence detection, where when you have one input, it has an oscillation, but when you have two inputs at the same time, the magnitude of the voltage increases. So that is what coincident detection means. When there are two inputs at the same time, the output, the changes in the memory potential increases. So it can limit the frequency. It can also perform input frequency preference. It can also develop memory, where you have a negative pulse, a positive pulse, and there's a combination of negative and positive pulse. So it has all the memory encoded in itself, and it can also sense calcium and amino acid, where with changes in the concentration, it shows the different behaviors, different structures in uh, the profile, in the action potential or oscillation profile. Now, since all these kind of behaviors are possible, and we are the authors are actually changing or playing with the concentration of the electrolyte, we can actually interface that with a living tissue and see how that can behave. So going forward, the authors actually performed or interface the entire circuit, specifically the sodium OECT, with the vagus nerve of a rat, where they were actually playing with the concentration of the sodium in this OECD. So when the levels were normal, there was no spiking that was observed in the device, and we can continuously monitor the heart rate of uh, of the rat, of the living rat, during the experiment. When the levels were increased from 25 millimolar to 100 millimolar, there was spiking observed in this circuit, and there was a reduction in the vagus nerve, reduction in the heart rate of the rat. So it can perform sensing of the biochemical signals and also help in stimulation. So this kind of polymers, which can operate at an environment which are physiologically relevant and can also sense and stimulate by interfacing with the real neurons, this field is what is called as bioelectronics. And neuromorphic devices, so the device here is not only capable of helping to mimic the neuron, it can also interface with the living tissue, where it can sense and also stimulate at the same time. So this kind of operation and this kind of behavior in this class of transistors, this class of devices, is very interesting, and this has been a topic of research now. And it feels like it can do several things. This kind of devices can actually perform several many different kind of applications. So to conclude my talk, I was talking mostly about like how the organic electronics, specifically the polymers, how polymers can help in transportation of the electronic and charge carriers in its in the channel of the OECTs, and how the OECTs can be used to mimic the neuronal behaviors in neuromorphic devices. With these devices, the organic electrochemical transistors or OECTs can be used to develop several logic gates, and with proper connections, we can even mimic or even we can model the action potential in a Hodgkin-Huxley circuitry. And then apart from computation, which so that this by not only making those integrated circuits and devices or chips, you can even interface these devices with living tissues, where you can biochemically record the signal and process the information at the same time, so you can get an actionable response out of it. Hope you enjoyed the presentation. Thank you.